Today, Wojtek is going to present us the ML monitoring flow. Wojtek is one of the founders of NaniML, and NaniML is a Python open source library to monitor all your models in production. So yeah, I can tell you that you are going to be in very good hands. And of course, if you have any question during the webinar, feel free to drop it during the chat. I'll be trying to answer the question during the webinar, and also we're going to have some time at the end. So yeah, Wojtek.
Yeah, thanks a lot for the introduction, and let's get started. So yeah, today we're going to talk about the ML monitoring flow, and let's get started with a quick agenda. So yes, the agenda itself is the flow, and as you probably already read in the description, we're focusing on the performance monitoring first. So when you deploy your machine learning models to production, the main basically goal of doing anything after the deployment is to make sure that the performance of your model stays satisfactory and ideally not only stays as good as it used to be or even improves. And the first thing that we need to do to really ensure that we meet that goal is to monitor that performance. So this is the first step. Then if we see that there's any issues with performance, we're going to figure out what caused those issues. And that brings us to the second part, which is the root cause analysis. When we will use tools like covariate shift detection to figure out what actually went wrong with our model or our data. And then after we nail down what's the actual problem, we can go to our third step, which is the issue resolution. And of course, this flow is iterative, and it basically forms a framework of how you should go about doing your ML monitoring or doing your post-deployment data science. First, let's quickly go over the goals of why do you actually need to monitor your machine learning models. So the first and the most important thing is you want to maintain the business impact of the model. As a data scientist or as a head of data science, your goal in your job is to basically create as much business impact as possible via machine learning models. And step one of that is to develop those models, identify use cases, develop the models, make sure that they are actually validated. And the step two of that is to maintain this business impact after they've been deployed to production. And for that, of course, we need to monitor our models. Second thing is, because our models work in real life, they interact with real world, there might be some dynamical system behavior there. And also, of course, the actual model works on data that's not perfectly valid, not perfect in every sense. There is some stochasticity, there is some randomness, maybe some data quality issues. There's always a risk of associated with the model. So imagine that you deploy a model that automates certain process that used to be done by humans, let's say insurance pricing. And you manage to improve the performance of that pricing and you outperform human evaluators. However, in time, your model decreases and the performance of your model decreases. And the performance might decrease so much that actually, instead of bringing business value, you are reducing the business value and you're not as good as human evaluators. So it would be better to not have this model at all. That's an example of a risk that every model that's deployed to production poses. And the second goal of monitoring is to reduce that risk. And then the third one, more from kind of personal perspective, is for you as a data scientist, again, or head of data science, you want to increase the visibility of your model and the business impact brings, because that might bring you promotions, that might bring you raises, that might bring you more budget to your team, or just recognition in the company. And it's, of course, fulfilling to see that other people also appreciate your work. So these are the goals. Now, how do we go about it? Let's get started with the process very quickly. Again, I'll start with performance monitoring. The first step here, we're going to focus on performance calculation and performance estimation. So two main ways that we can actually monitor performance. We can do calculation if we have ground truth, and we can do estimation if we don't. And now let's take a look at the actual flow here. The flow here. So when we try to monitor the performance of our model, the first question we need to ask ourselves is whether ground truth is available. And if it is available, then we can just quickly calculate the performance. By performance, I mean any technical metric or business metric that you use to evaluate the quality of your predictions. So let's say for binary classification, this can be your F1 score. It can be actual dollar amount saved or made by the model if you can estimate quickly based on your confusion matrix. For regression, it would be maybe mean squared error. Any metric like that that actually evaluates the quality of your predictions, the predictive performance of your model is what I'm talking about here. And if we have access to ground truth very quickly and fully after we make the prediction, let's say in high frequency trading, then we can monitor the performance just by calculating it. However, in most of the use cases, we do not have access to that. And in that case, we need to go into performance estimation. And when we estimate the performance of the model, we're trying to use other signals in our data to figure out what is the expected performance of our model based on basically the distribution of our model inputs and what our model thinks of them in a way. And here we have two algorithms that we came up with. For regression, the direct loss estimation algorithm, and for classification, confidence-based performance estimation, which are again algorithms that are available in our open source in NaniML. And we're gonna go over those and kind of quickly build intuition of why these, of how these algorithms work and how is it even possible to estimate the performance even if you don't have ground truth available. So for the, just one quick question, one quick thing to mention before we go into the regression and our first algorithm DLE. The main reason why we normally need to estimate performance and we can calculate it is that we tend to predict things that are in the future. Let's say you predict something that will only happen in a month, and you really need to know whether your models are performing well as soon as you possibly can. So before we get access to ground truth, even if that ground truth can arrive, we need to estimate it sooner rather than later. And in some other use cases, when trying to automate something, again, insurance pricing is a good example, then we will not get access to full ground truth at all, because doing that would just defeat the purpose of automating a system. And of course, we can do spot checks here and there, but it will not give us the full picture of what is the performance of your models. So we need to resort to performance estimation. So now let's get started with regression. And for that, we have our algorithm DLE, direct loss estimation. And here we can estimate basically any metric that you use to evaluate from technical perspective the performance of your algorithm. So MAC, MAE, logarithmic error, any kind of error that you will compute on instance level. And what we get out of it is a simple plot, of course, associated data frame, where we get our MAE, we get estimation of error of our estimation. So you can also see how confident the algorithm is in making the predictions about the performance of your models. And we automatically determine the threshold, which is the red dotted line there. And if the performance goes above or below that threshold, in the case of regression, it goes above the threshold, then we're getting automated alerts. So let's quickly build the intuition of how is it even possible to try to estimate the performance of the model if you don't know what's the ground truth for every single prediction. So here, let's build our intuition first on a 2D example, actually 1D example, when we just have one feature and we have quite a bit of noise and we're trying to predict our target. And we see that there is some kind of relationship, so we can actually build some kind of model that would predict the target. And of course, it's not going to be a perfect prediction because we see that the data is noisy. And another interesting thing that we see here is that as we move from left to right, so as the value of feature one increases, the data becomes more noisy. So the level of noise is also dependent on feature one. And that means that our predictions will generally be better on the left side here if the value of feature one is small. So what we can do is we can build a model that takes this feature one and tries to predict what is the absolute error or squared error of this prediction. And we see here that as it increases, the error increases, and it's actually an information that is contained within the dataset. And it's something that's, of course, very easy to do for one feature, but the same principle also applies if we have 200 features. We can just take all the features of our model and try to look whether there is inherent uncertainty or the level of noise is higher in certain regions in our input space. And then based on that, we can predict the estimated loss for every single data point. And of course, this is going to be very bad prediction or a very noisy prediction as well. But if we aggregate it for quite a lot of points at the same time, we can get a reasonably good estimation of our performance. So let's continue with the intuition here. And one important thing to mention is that when we build this model, we need to have some kind of data to build this model on. And this is going to be our reference data set. So ideally, this would be our test data for which we evaluated our model. We know that the performance on this test data is good, it's satisfactory, we were happy with it enough to actually deploy the model. So we know it's all fine there. Data distribution is fine, the performance is fine, data quality was also quite high there. So we take that our test data, and for every data point in our test data, we're going to take the prediction that our model has made. We're going to measure the error there for regression here. Let's say we're going to measure the absolute error, and we're going to treat it as the target for our DLE. And then you see here that there's going to be some regions when there is more uncertainty in the data as to there's less information in the data about the target in certain regions in our input space, to phrase it more clearly. And we have some kind of distribution of data points in our test data. And then we see that there is some kind of covariance shift, so change in the joint model input distribution. Our features look different, they're distributed differently between our test and production data, which is something that's going to happen all the time, but it does not mean that the performance of our model is changing. However, here we can actually quantify whether it's changing and by how much, because we can just estimate for every data point in this space what is the expected performance. And if we see that there is more data points that drift towards regions when the expected performance is lower, we're gonna expect a drop in performance. And by building this model that I mentioned, we can actually quantify it quite precisely. So now let's look at the kind of recipe for the algorithm and how we're actually gonna do it step by step. So first, we're gonna calculate the loss metric on our reference data on our ideally test data set. Let's say absolute error. Then we're going to train the model to estimate this loss metric. And we're going to use our features for that. And we're also going to use monitored model predictions. And the reason we use monitored model predictions is that sometimes the problem of finding what's the uncertainty and finding the actual target is quite related. So we can use it as a very strong and very powerful dimensionality reduction technique. And just in practice, empirically, we see that these model predictions tend to be very informative feature, more than other features when it comes to estimating the error. And then for every single data point, we can estimate the error. We're going to then aggregate it for certain chunks of data. Let's say you want to do your monitoring every day or every hour or every 1,000 data points. We're going to then aggregate this error. And then basically, NanoML is going to give you the point prediction for your, let's say, MAE, so mean average error, and it's going to give you also the uncertainty. And this uncertainty is strictly dependent on the size of your chunk or how you aggregate the data. So if you have more data points in your aggregation, then the noise is going to kind of even out and we're going to get more precise prediction. So then you as a user need to look at the business requirements. If you need to look at your model performance daily, but you only have 50 data points every day, it might lead to quite a high error. On the other hand, if you have, let's say, 20,000 data points every day, then it's going to be perfectly fine to look at it daily because your error bands are going to be very small and you're going to get very confident predictions. So now let's move to the second algorithm, which is the CVPE for classification models. So here, important thing to mention, it of course works both for a binary classification and multi-class classification. And what can we estimate? We can estimate the confusion matrix, and then we can estimate literally any metric that stems from the confusion matrix. So precision, recall, accuracy. The metric starts with S, I cannot pronounce it, F1, etc., etc. And we can also estimate ROC AUC, so basically all the metrics that you typically use to evaluate the quality of the predictions. On top of that, we can also estimate business impact specifically for binary classification models and multi-class now. That if you can evaluate the quality of your or the business impact of your predictions just by summing up the elements of the confusion matrix, quite possible. I'm going to give you an example soon. Then you can also estimate them. And the example is as follows. Let's say that you do default prediction. For every false positive, you're going to lose $20. For every false negative, you're going to lose $10,000. For every true positive, you're going to make $100. For every true negative, you're making $0. As an example. We can actually also just sum it up and get certain metrics that's expressed in dollar amount, and that metric can be estimated with CBP. And then you can actually show that directly to business stakeholders to tell them how much money your model is making. So now I'm going to skip the intuition since we have quite a lot of ground to cover, but the intuition is very, very similar. You, again, look at uncertain regions in space, and then you quantify what is the expected error there, and then we aggregate the results. And I'm just going to give you the recipe for the algorithm since it's slightly different. So here, we're going to use only the model output, so the model predictions. And we're not going to use the model predictions that are binary, so 0 and 1, but we're going to use the model scores. So the number between 0 and 1 that you get when you, for example, in scikit-learn use .predictproba. We're going to calibrate those. So we're going to turn the scores into actual probabilities. Without going too much in depth, sometimes the scores actually don't represent real probabilities. So if you have a score of 0.1, it does not necessarily mean that if you get 1,000 scores of 0.1, 10% of them will turn out to be positive. So we need to make sure that this actually holds and we can interpret these scores as probabilities. Then I'm going to choose a threshold that was chosen also by you as a model developer, for which every prediction above that threshold is going to be classified as positive. Every prediction below that threshold is going to be classified as negative. Same hold with a bit more wriggling here and there for multi-class classification. Then for every data point, we're going to find the expected confusion matrix. And the way we do it is we're going to do it the exact same way as we normally calculate the confusion matrix, but instead of taking the predictions, we're going to take the probabilities. So if the probability is 0.7, and we know that it's a positive prediction because let's say our threshold is 0.5, then we know it's a positive prediction and it has exactly 70% chance of being true positive. So putting 0.7 in true positive and 0.3 in false positive. And we have this partial confusion matrix for every point. And of course, this would be a terrible measure. But if we aggregate it over a few hundred or few thousands of data points, we're getting quite a good estimation of whatever metric we're trying to find. That's how the algorithm works. Now, we know how to estimate performance. I will not cover the performance calculation because that's trivial. You just get the metric and you get the output, and the output is going to be exactly the same. And of course, you can do it via NaNiML. Now, let's jump to the second part of the process. Imagine that there is a drop in performance. There is an issue that we need to basically resolve. Then what we need to do is we need to figure out why this issue happened. So the root cause analysis has a kind of a mini flow inside it, where what we need to do is basically 3 steps. First, we're going to run drift detection algorithms, and we're going to run data quality monitoring algorithms. They're again available in our open source library. Then we're going to see what are the problems there, what data actually drifts, what distributions change, whether we have increase in, let's say, missing values, whether we have a lot of unseen values, etc. We're going to correlate those drift signals and data quality signals with performance to try to figure out which of those might be causal or might be strongly correlated with performance. And then we're going to have to use our domain knowledge to figure out whether some of them actually are the root cause and what can we do to resolve the problem. So quick overview of possible drift detection and data quality monitoring tools at our disposal. The first thing is univariate drift detection. where we will just look at the distribution of a single feature, whether categorical or continuous, and we're going to compare the distribution of that feature with our test data distribution. So again, the reference data comes in handy because this is the distribution in which we know everything is fine. And there is a couple of problems with that because you get so many false positives. Imagine you have 200 features and they will, of course, drift here and there, but it doesn't mean that they actually cause any problems, which is one of the main reasons why we actually need to estimate performance and we cannot just rely on drift detection, because you will just drown in alerts that don't correlate with performance, don't cause performance degradation, make performance is completely fine. And that's why we always start with performance estimation, and only if there is a problem, we need to dive deeper into all the drift detection methods we have at our disposal. Then we have the multivariate drift detection that I will cover in detail very soon. And there, what we can do is we can look at any set of features and we can look at how the structure of the data is changing. So we can look at all the features at once or basically any subset of the features that our model consumes. And this is quite useful because we are able then to capture the changes in the correlations or relationships between features. And those relationships might be more important than the features themselves, depending on the problem type and the model that you're using. And the last thing that we have at our disposal is data quality. And here we keep it simple. We're going to focus on two things. If we have more unseen results that we haven't seen before, or missing data. And of course, even if our algorithm can handle missing data, if there's a lot of missing data, it might mean that if the feature was strongly predictive, the performance will decrease. So let's look at the most interesting algorithm and the one that I recommend that you use basically first to figure out what's going on certain subsets of data, which is the multivariate drift detection. And let's take a look at what we see here. It's going to be very similar to our performance estimation. When again, we have certain drift measure, which is called reconstruction error. And we see its performance on reference data, which is the first part of the diagram in bright blue or light blue. And here we have our reconstruction error that we see after the model has been deployed to production. And we have it in data chunks. So again, we're going to aggregate it, let's say weekly or daily. And if it goes above or below our thresholds, then we're going to say that there's an alert and we can correlate those alerts with performance. Interestingly, of course, you can change these thresholds to better suit your needs. Same for performance, but they are by default determined automatically, and they are determined by basically the variance of the reconstruction error in our reference data set. So these are the results. Now, what does it actually do? It can capture any linear change in the relationship between features, which is quite useful, again, because they might be more important than the features themselves. But it also captures that. It also captures changes in single feature distributions. It's a multivariate approach, so it requires at least 2 features to work. And it has only one downside, which is not easily interpretable because we're just getting a single number that represents change in structure in our data. So let's delve deeper and build a bit of intuition about how this algorithm works and why it's quite useful for determining whether there is data drift that can be causal of performance drop. So here is the intuition. We take our original data, which lies in a certain manifold, it's distributed in some way. We're going to compress it. We can compress it using autoencoders. We can compress it using PCA. Right now in our open source library, you have the PCA compression because it's incredibly robust. So we're going to train a PCA on our test data and we're going to compress the data. Then we're going to train an inverse transform and we're going to reconstruct our data. So what happens is basically our compressor decompressor learns the internal structure of the data in a way that maximizes its ability to reconstruct the data correctly. And then we're just going to simply measure the difference between our original data and our reconstructed data. And that's the reconstruction error. And this is something that we use as our drift measure. And if the structure of the data changes, let's say the linear relationships between features change, then our compressor decompressor will no longer be well suited to compress and decompress this data because it's been trained on different data set. It learned a different structure. So then we can actually see the change in the structure. There's one interesting thing here is that there is also a lower threshold, and it's kind of an edge case, but we see that a lot, especially if you use this algorithm for computer vision data. So if you work on images, you will see that quite often the reconstruction error actually drops. And that means that the structure of the data becomes simpler. And this is quite often the case with real life data sets, that you train it on as many diverse images as you can, and then you get the exact same type of image over and over again in your application. Let's say for Zoom that we're using, basically you have background removal, and it's going to be people sitting in chairs with stuff behind them. So it's going to be actually much simpler distribution and much simpler images than on your training data. So the reconstruction error will drop, and that also indicates the drift in your data. And just because the structure is simple, it does not necessarily mean that the performance is going to be better, because maybe these are simple pictures when it comes to the structure, but they don't hold much information about the target that we're trying to predict. So with that in mind, we covered the most interesting part of root cause analysis. Before we jump into the last part, which is the issue resolution, let's see how we can basically bridge this gap going from the root cause to issue resolution. What we can do is we have a few algorithms. Again, in interest of time, I will not cover them in depth, but we have a few algorithms that allow you to correlate, starting with simple Pearson correlation, all the signals that you get from data drift. So you take data drift outputs, you put it in so-called rankers, together with whatever performance you're interested in, let's say MAE, and you'll get ranked results of what are the potential causes in terms of features, data quality, whatever you put there, of your drop in performance. So we identified what are the potential causes of the problem. Now that we know the causes, we can actually resolve them. And here I will quickly go over potential basic ideas. We can retrain the model. This is the first step. Simply add. It is, of course, something that is kind of a default step, but it doesn't always solve the issues. And then we just automatically retrain the model. We validate whether retraining was successful. We put it back to production. We can adjust downstream processes. Let's say that we're doing credit risk assignment, and we see that our performance is not as good as it used to be. Then we might want to decrease credit line assignment. We might decrease the credit that we assign to our customers across the board if we know our performance is no longer as good as it used to be, to reduce our general risk exposure. If we automatically retrain our models, we can revert to a previous model if the new model for some reason does not perform well anymore. If things are going really bad, we might need to refactor the entire use case, or we might do nothing. Now let's look at the stable and go over them kind of step by step and dig a bit deeper and figure out basically when we should use them, when we can expect it to work, and what are the potential obstacles or things to be mindful of. So when it comes to retraining the model, if we see that the performance has dropped, the default first step is to retrain the model and see if the retraining was successful in a way that it actually increased performance. However, it only works if there's concept drift, because if there's no concept drift and the performance degradation is due to covariate shift, so the data is just harder to predict on, there is more uncertainty in the data has drifted to regions where there is less information, retraining the model will not fix that. But if there's concept drift, so change in the relationship between model inputs and the targets, retraining will be able to actually capture this new concept and will be able to resolve our issue of performance drop. And interestingly enough, it's something that we actually saw with quite a few of our users. Automated retraining might actually make matters worse if root cause is the data quality issue, because you will not only predict on data that's low quality, which caused the drop in performance, but you will retrain the model that's on the data that's low quality, and then all your future predictions will also be of lower quality. So you might enter a negative kind of feedback loop if you don't take care of your data quality first. So automated retraining and deployment is probably not the way to go in vast majority of the use cases, and you really need to have automated checks whether your retraining was successful or not before you redeploy the models. Then second thing we can do is basically adjust the downstream processes, like the example I already gave. And the goal there is that if we cannot fix the performance degradation, because maybe it's due to pure covariance shift, people are just harder to predict and they're less predictable. Maybe our segments switch, and it's mostly the segment that it's the hardest to predict and that we're working with right now. The only thing we can do is we can minimize the impact on the business processes downstream. And there's two ways of doing that. We can generally just involve humans in the loop, so they validate the most important predictions or the predictions where we expect the performance to be the lowest, or we can adjust the actions that are done based on the predictions. So again, like I mentioned, we can adjust, for example, how much credit line we assign to each of our customers. If we do automatically retrain our models, and hopefully there is some kind of champion challenger system there, we can revert to a previous model if we see that our new model, even though it was initially performant, suddenly performance dropped. It might be a quick fix, but again, of course, you need to check if the previous model is still performing, because again, it might be that all of your models are not performant anymore and the failure is not that easy to fix. And if that is the case, then we need to go into our fourth way of solving the problem, which is refactoring the entire use case. So basically, that means that we need to engage ourselves as data scientists or other data scientists again and try to redevelop the use case, not fully from scratch, but maybe change the model type, the hyperparameter settings, the features that we use, etc., etc. So this is costly, but chances are it will work. Of course, ideally, we should gather more label data before we do it, because it might be that we already are doing our best and all the effort spent there will not really yield any improvement. And if the main cause was pure covariance shift, then it still might not work. And the last thing, but it's still a very reasonable thing to consider, and it's an important thing to consider, is that sometimes if the performance impact is not severe enough, the best thing is to do nothing, as long as you can actually know that this is the impact, this is the drop in performance, we can evaluate it, and we actually make a cost-benefit analysis, and we see that it doesn't make sense to do anything about it. And the main reason to do nothing is that fixing costs are higher than leaving the problem as it is. It might be that we need to fix the problem, we need to gather a lot more new label data. And for every data point, we need to pay insane amount of money to actually label it, because we need to do, I don't know, scientific experiments to get new data. And in that case, it doesn't make sense to actually fix the problem. It might be that the administrative costs and bureaucracy is blocking us from actually retraining the model or fixing the problem, because we work in a very heavily regulated industry. In that case, just knowing what is the issue and adjusting downstream processes, or just knowing it and communicating that to all the relevant business stakeholders might be enough. And that's it. That's the end. So let's just summarize now, and then we can have a few rounds of questions. So key takeaways. The three-step monitoring flow that I outlined here ensures continued performance of your model, and this is the main goal of your ML monitoring and generally post-deployment data sets. And the first part, which is the performance monitoring and estimation, are crucial and cannot be replaced with data drift detection, because then first, we don't know whether our business impact is still as good as it used to be. And secondly, sometimes, quite often, actually, data drift will not cause drop in performance. And thirdly, data will drift all the time, so we'll just drown in false positive alerts that will not tell us anything, causing us to just stop looking at it completely. However, data drift detection or covariance detection is still very useful, mainly as a root cause analysis tool, because it allows us to figure out what exactly went wrong with our data and our model. And one last important thing is that retraining is not like a golden cure. It will not always fix your problems and can be even a source of an issue or it can deepen your problems if data quality is at fault. So that's it. Thanks for listening. We're going to have a quick round of Q&A, and do check our GitHub. As Santiago already mentioned, we're free, we're open source, and this webinar is also more or less the same content, but going slightly deeper, I would say, in it is also in the form of a blog on our website. So feel free to check that out. And if you want to receive the recording, just scan this QR code and you'll be able to get the recording. So thank you very much. And back to Santiago to do a quick Q&A.
Yep. Thank you. Thank you so much for the webinar. We have right now 3 questions. First, one from Alexander Valverde. He's asking, how can I measure the drift for a CNN classification model? If my images come from Facebook posts and can vary because designer ideas, is there a good idea to use the same techniques you're explaining, or do I need to use something else?
Yeah, that's a good question. So right now, what I would recommend is definitely don't touch univariate drift detection, because then you're going to do it pixel by pixel and you're just going to get pure noise. But our multivariate drift detection still should work, and we actually saw quite a lot of users use it on generally computer vision and convolutional neural networks. So you can basically use the exact same algorithm, and as long as you can just represent your image as a matrix, you can feed it into our algorithm, which is what you need to do anyway to actually feed it into a convolutional neural network. So you can use that, but only use multivariate drift detection. Univariate drift detection is pretty much useless when it comes to computer vision models.
Second question is from Hirek, and I hope I'm pronouncing it correctly. He's asking, for multivariate drift detection, how do you determine the dimensionality of the latent space to be used?
Yeah, so here, basically we do it automatically based on the number of variants kept. So quite simple heuristic. An interesting point is that we don't actually care that much whether the our PCA captures a lot of variance and it's a good encoder. We just need to establish a baseline that's good enough and captures some kind of data structure. If it captures more data structure, it's going to be more less robust or more brittle for small drifts. If it doesn't capture enough of the data structure, so it doesn't capture enough of the variance, it will not be able to capture smaller drifts. So there is a bit of back and forth there, or there's like a point when you try to optimize it for, and it's not capturing all the variance. It's capturing empirically around 90–80% of the variance, and it's done automatically in NanoEML. It's also just a hyperparameter that you can change.
Nice. Another question from, okay, it's a username that I'm not gonna spell. He's asking, this person is asking, could you explain why do you prefer PCA to instead of autoencoders for multivariate drift?
So it's not necessarily that we prefer it, but it is an option that just works very robustly. We're actually currently working on also including autoencoders. But the reason we went with PCA is that it's a simple algorithm, that it is incredibly robust to any kind of data. And because we're an open source library, we basically need to provide a solution that works for any kind of data that you put in there. So we need to have robust AutoML behind the scenes. And as I already mentioned, for the encoder decoder, we don't actually care that much that it's the best encoder that we can possibly make. We just care that it's good enough and it captures the right amount of structure. And we just found that in our experiments across different types of data, different data sets, different dimensionality, etc., PCA performs extremely robust. But we're still working on autoencoders, as autoencoders have one extremely important feature that PCA doesn't have, which is that it can capture any kind of structural change and not only linear changes in the data structure. So this is definitely a drawback of PCA and an advantage for autoencoders. And it is the reason why we're still working on autoencoders. On the other hand, autoencoders take a lot of work to be robust and to work with basically any data volume, any data dimensionality, any data structure that you throw at it. And here we're going to go obviously with variational autoencoders because they are a fair bit more robust to noise and small changes in the data distribution than traditional autoencoders.
Thanks. And let me check if there's any more questions. So far, there's no other question. I'm gonna put in the chat a link to the NaniML Slack community in case you can think of if in case you have any other question after the webinar ends and you still want to ask us something, feel free to join. And usually we are all there with other data scientists in the community, and we're always very happy to meet new people.
Thanks a lot, everyone, and hope to see you in the community on LinkedIn or anywhere else.
See you. Thank you.
Bye.